Welcome you to today's webinar. Today we will be discussing the integrated MPPT algorithm found in FRONIUS inverters, which is called the Dynamic Peak Manager. And we'll have a look at all its features and how it can benefit the user. And we will also have a look at the different shading effects and the measures that you can take to counteract any negative shading effects on a solar system. First, I'd like to introduce you to the team today. I'm Mohammed Sidat, the Technical Sales Advisor for Southern Africa. I am from FRONIUS South Africa. I'd also like to introduce my two colleagues, Sipho Nakolo. He is the TSA from Western Africa, Technical Sales Advisor. And I'd also like to introduce you to David Mwangi. He is the Technical Sales Advisor for Eastern Africa. Okay, both my two colleagues are from FRONIUS International. I'd like to also introduce the agenda to today. We will first start off with shading and the possible causes and effects. We will then move on to string series orientation, after which we will have a look at the uses of a bypass diode. And these first three topics will be covered by my colleague, Sipho Nakolo. After which David Mwangi will take over and he will talk about the Dynamic Peak Manager and integrate and show to the audience how this is a very effective FRONIUS solution for counteracting shading. He will then move on to smart modules and talk about the uses of smart modules. And we will then compare the Dynamic Peak Manager versus a module-based optimizer. After which we will then go through a quick summary and we will then stay behind for about 10 minutes after the presentation to answer any questions. So I'd like to hand over to my colleague, Sipho Nakolo, who will take over this first half of the presentation.
Hey Mo, thank you very much for the introductions. Good day, everyone. Good morning, good afternoon, good evening, wherever you are. It's a pleasure to have you all around today for this presentation discussing about the Dynamic Peak Manager. And yes, so we're going to start off with the different types or forms of shading. And we'll start off immediately by looking at how this can actually occur. Yeah, it's a good thing that for every part of the world, we have the privilege of having sun irradiation or sun. So of course, we then have the opportunity to harness the power from the sun. Let's see if I can get my pointer here already. Okay, yeah. So, but then we have different reasons or causes of shading on this module. This can result from superstructures, dirt, snow, chimneys, trees, cables, or electric poles. There's so many different causes of shading. So, but then how can this be resolved? So that is what we're going to be looking in. And in the long run, will now introduce us to the integrated shading solution from FRONIUS, which would serve as the best way to mitigate the effects of shading. So we can now continue. Yes, so depending on the percentage of the shaded area and the frequency of occurrence, that will give us the yardstick to differentiate between low, moderate, and then strong shading. Yeah, as you can see from the references below, some we have an example of a low shading, and then moderate shading, and then strong shading. So, but then the most important thing here is to ensure that during installation, we do our findings and then try as much as possible to avoid it in the first place. So, but at the end of the day, what does this cost? The effect of shading is simply, apart from the debilitating effect on the modules themselves, thereby reducing their lifespan, per se, it also, most importantly, causes less yield. So you'll have less yield, and this will in turn result to a longer return on investment period, which isn't what we would like. So let's say, for example, if it's supposed to take you, let's say like 4 to 5 years to achieve ROI period, it now takes longer because of shading. So this presents a very, very big challenge. And then, of course, we'll have to do everything in our enablement to see how we can mitigate the effects of shading. So, like I said earlier, good planning helps to reduce the effects of shading. So the first question we need to ask ourselves is, during the design and during the layout plan, we need to have a well thought out design that would avoid shading, occasions of shading. Let's say if you have a superstructure, a tall structure beside the building that casts shade or shadow on your roof, or be it chimneys or be it electrical poles, it now behoves on us to see how we can avoid these shaded regions. Most importantly, during periods of high irradiation. So, in order to give us an in-depth view of what happens during shading, we have this representation of strings of modules connected to a string inverter. And let's say in this case, we have a shadow being casted on the particular module. And being the fact that these modules are actually made up of smaller series connected cells, DC cells, it simply means that if this module, as you can see here, if this module here is completely shaded, it in turn blocks the flow of current for this entire string. So that means that this entire string is affected, and there will be no output from this entire string because of the shading on this particular module. So the shaded module acts as a bottleneck to the entire string. And as you can see from this illustration, yes, the shading here automatically increases the impedance, that is the resistance, which is measured in ohm, as you can see here. So once there's an increase in resistance to an infinite level, as you can see in this case, there is a complete blockage of current flow, and then of course would have no output. So we'll now take a closer look at string series orientation. Yes, I believe we're all conversant with the relationship between power, voltage, and current. So in a series connected array, as you can see, voltage steps up from module to module, but the current remains constant. So if there is any impedance at any point in this series connection, then there will be a resultant decrease in power, of course, resulting to the decrease in current flow, all proportional to the level of impedance presented on this series connection. So to further explain this the more, would use a module IV curve to explain this, a module current over voltage curve to explain this, and using the test with standard test conditions, we can see that the current is proportional to the irradiation level. So we have a region where we have a high irradiation, in this case 1000 watts per meter squared. So in this case we have excuse me, we have a current level of up to 9 amps. And then the maximum power point for this particular curve is about, let's say 32 volts. Yeah. So, but then if there is, let's say, shading or complete cloud cover, this can actually drop to as low as 200 watts per meter square. And then once this happens, of course, it results to a sharp or steep drop in the current output. As you can see, it drops dramatically from 9 to about 1.6 amps. And then, of course, this leads to low irradiation level. Excuse me. So another thing, so this basically tells us that the lower the irradiation, the lower the current. Then the higher the irradiation, the higher the current. And then one very important point to note here is that there's only a minimum change, a differential change in the voltage level when all these are happening. That is between the drop from 1,000 watts per meter square irradiation level to 200 watts per meter square irradiation level. So as you can see, if we look closely here, we can see that the drop in voltage, the differential in voltage level is say 28 to let's say about 32. So that's about just 4 volts, which is quite very, very minimal on the voltage side. So we can see that irradiation very, very much is very much dependent on the proportional to the current flow. So that is why it's very, very important to avoid shading as much as possible so that the maximum amount of power can be harnessed from the module. So as a first basic rule, as a summary, is to try as much as possible to avoid shading, especially at times, at the time of the day with high irradiation. And then if possible, remove heavily shaded modules from their installation point to see if you can move them to places or area where there is a good amount of irradiation. And at the end of the day, intelligent system planning and design is the key. You could do an assessment of the area. Of course, this can actually be overcome when you have maybe new constructions coming by, because you can have an intelligently planned system where you have all the roof well exposed, enjoying full irradiation, and then all of a sudden you have a new construction by the building side, and then you have maybe an electrical pole or a tree grows over the years and then starts casting shadow on this roof. So sometimes there's nothing you can do about it in terms of a shading, but of course with much intensive effort put to it, we can do our best to avoid such situations. So we would now go to the bypass diode, which is a component that plays a very, very important role when it comes to mitigation of shading. So basically, we'll start with the definition of the bypass diode. So these are unidirectional components that allows a series, or sometimes called a string of connected cells or solar modules, to continue to supply power at reduced voltage rather than no power at all. So these bypass diodes are connected in reverse bias mode between the solar cells, that is positive and negative output terminals, and has no effect on its output. So this might be maybe too much to comprehend, but of course we would have examples to explain this. So the bypass diode basically protects against damage in case of shading, and of course minimizes the impact on yield losses in the case of low shading. So it is actually implemented these days as a standard for almost every module that is manufactured. Yeah. So I would have a functional description, like I said earlier. So we can see here this components here are the bypass diodes. So just like the name implies, they tend to bypass any shading occurrence. So let's assume that the current is flowing from cell to cell, as you can see, represented by the eye, and then it encounters an impedance here casted because of a shadow or a shade casted because of a shading incident. So what the bypass diode does is once this happens, this junction becomes active. That is, the diode becomes active, and then the current can now pass through the diode, and then you can now have an output power that exempts this shaded cell. So instead of having no power at all, in the case whereby there was no diode, bypass diodes, of course, you can at least have the power generated from these three cells. So the positioning of the cell of the impeded cell does not matter, as you can see in this case. So even if the cell is in between, the current just bypasses it, flows through the bypass diode, and then continues. So whichever cell is impeded is bypassed automatically by the bypass diode, and then you now get an output that exempts the power of the shaded cell. So I believe that that's done justice to that, to explain how the bypass diodes function. So basically, the bypass diode's resistance, it's a bit conventionally, its internal resistance is a bit higher than that of the cell. So once there's no shading, of course, the current definitely passes through the path of least resistance, which is via the cells. But once there's a shade, this increases the impedance, and this impedance is definitely higher than that of the bypass diode, thereby making the current to pass through the bypass diode path and then following the other least resistance path. So that's basically it functionally. So effects and advantage. So if there's no shading, then of course the diode is inactive because its internal resistance is higher than that of the cell. But then if there's shading, then it automatically means that the impedance of the shaded cell increases and becomes higher than that of the bypass diode, thereby making current or forcing the current to pass through the bypass diode onto the other cells connected on the module. So the effect is it of course minimizes losses. The module string is hardly affected, and then the bottleneck created by this shading is minimized or mitigated to the least, and then protects against damage to the shaded cells. So having said that, we'll now take a look at module structure, module structures actually. So we're looking at model 1. Now for standard module structure, this is how they look. They're basically, like I said earlier, they're composed of modules actually composed of smaller cells, series connected, and then in batches of 20, as you can see in this example. So we have 20 cells here connected to a particular bypass diode. So 20 by 3 gives us 60 cells. So you can actually have 60 cell module or 72 cell. But in this case, we're using an example for a 60 cell. So once, let's say we have an impedance here, maybe a leaf drops here. So the series connection is cut off, and then we'll only draw power out of the 40 remaining cells via the bypass diode. So that's for standard module. But the practice these days by module manufacturers, which is actually a positive one, is the emergence of half cells. So these half cells are basically 120 half cells that in turn gives us, let's say, in this case, 20 by 6 half cells. So this basically means that these half cells are all parallel connected to bypass diodes. So as you can see, these are 20 cells. As you can see my pointer, we'll have another 20 cell and have another 20 cell. On the top side, then we'll have other 20 cells. So this 20 cells by 6 forms 120 half cells. So this basically means that across the middle, we have, that's judging, as in basically describing the structure. Across the middle, we have the bypass diodes situated there. So given the opportunity to harness power from both ends or from both sides of the module. Now, the next illustration will tell us how this comes to effect when it comes to mitigation of shading. Now, for a full cell shaded module, as you can see and as depicted by this illustration on the left, once you have a shading casted on by, let's say, a shadow of a tree or melting ice, it's going to cut off the entire bypass diode and you end up having zero power generated for this particular module. But then in the case of half cells, in the same condition, if you have a casted shadow by a tree or melting ice, only 50% will be cut off. Only 50% power will be cut off. So you can be sure that you have 50% power generation from this module because of the half cell structure, as you can see. So this in turn very, very much mitigates the effect of shading on module. So yeah. Before we continue, I would like to launch a poll. So let me know. I'm going to launch a poll now to get your experience from your installation. So do you experience shading in your installations? So you can either answer yes or no. So I'm going to leave the poll for, let's say, another minute so that we can garner as much response as possible. Yeah, because shading is actually one of the challenges that is being faced by installers, and we're doing everything we can to see how we can mitigate it as much as possible. So by getting your opinions from these polls can help us to make informed decisions about them. So we'll be closing the poll in 5 seconds from now. Okay, so from the poll results, wow, we have a high percentage that actually experience shading in their installation. So this represents a very, very burning, a serious topic. And the good thing is that FRONIUS, in its, I would say, incisive ingenuity, has a solution for this to mitigate shading. And this would now be treated as by my colleague, David Mwangi, whom I will be handing over to. So David, you can now continue with the rest of the presentation.
Okay. Okay, so thank you very much, Cyprian, for the first very nice part of the webinar. So I'll be taking you now through what are the solutions that are possible to mitigate the yield losses caused by shading. My colleague has already spoken about the use of bypass diodes, and from the poll that has just been launched, we've seen that really quite a number of installers have some experience with shading. And the fact about shading is that pretty much you can have a very good design and you do not expect shading, but some of the shading is totally unavoidable, and therefore we need to look at how, even with this unexpected shading, how to maximize yield from your solar installations. So I'm hoping in the next couple of minutes, I can take you through how this is mitigated. So ordinarily with most electronic equipments used for harnessing PV power, the maximum power point tracking technology is used a lot, and this also is very common in solar chargers for, let's say, off-grid installations, but it's also a standard feature in most string inverters. So as already mentioned by my colleague and highlighting what is the maximum power point in an IV curve or the power voltage curve over PV module, most of these gadgets are looking for what is the best operating point to be able to deliver as much power to either the batteries if you are charging batteries, or to deliver as much power to whichever loads are utilizing that particular power at that moment. In this scenario, we are looking at an example that is showing 3 possibilities during the day. We have from around 8 in the morning, this black curve with shading, and we are seeing 2 different kind of MPPTs, which you are going to look at in the next slides. And then you have another example at 9 a.m. that also has 2 different maximum power points that are possible in the IV curve, and also another output at around 12 mid, which has really no shading and is giving the best maximum power point for this production. So in a nutshell, the MPPT algorithm basically scans the IV curve and is trying from time to time to find the optimal operating point, or what is called the global maximum power point. Going further, let's look at what are the potential pitfalls of ordinary maximum power point trackers. In case of shading, most trackers that are not intelligent enough are going to be stuck at what is called the local maximum power point. And this happens because when the tracker shifts, the operator tries to shift the operating point downwards or upwards, these 2 arrows indicated, it realizes that the power output is dropping, and therefore it's locked to what is the local maximum operating point. So this is not the best scenario, because this is not going to, if you look at this curve, is not giving you what is possibly the best output from this power module or PV array at this particular time of the day, even with shading. Because as we can see on this side of the power PV output, we have the possibility of up to 2 kilowatts. And for the time period 9 a.m., we have a higher point that could be giving us just about maybe 0.8 or 7 kilowatts. But because the MPPT tracker is being cheated or is not intelligent enough, it's only giving you just about 0.5 kilowatts for this particular moment. So to address these problems, FRONIUS has an intelligent solution, and we would like to show you how you can benefit by using FRONIUS string inverters in your installations, because these are going to offer really very cost-effective means or methods of addressing partial or low shading conditions. So what is the dynamic peak manager? So in a nutshell, this is a new algorithm for maximum power point tracking that dynamically adopts its behavior when searching for the optimal operating point. And the optimal operating point is what we call the global maximum power point. By using the FRONIUS dynamic peak manager, you can be guaranteed of maximum yield even with low shading. Something else that I can mention here about the FRONIUS string inverters is together with global maximum power point tracking, the inverter itself has another feature inside that electronically is able to boost the voltage that is coming from the string arrays. So this ensures that the maximum or the MPPT operating point inside the inverter is as close to the optimal operating point as possible. And when you look at your inverter, you can see this kind of symbol at the top here, and this will tell you that this inverter has the dynamic peak manager integrated. And this is actually a standard feature in all FRONIUS inverters. Going forward, let us look at a best practice example to be able to understand what is happening really when you have a PV system with shading. So in this particular example, we are considering an installation that is just about 3.3 kilowatt peak. So it's not really a very big installation. This is typical, maybe residential installation. And this has a southwest orientation with a tilt angle of about 19.5 degrees. And it of course has a bit of shading for a particular period of the day, which you are going to look at in the next slide. And you can also see, because of this peak of the roof here, you have some shading early morning hours. So the effects of shading in this particular installation, we have shading, partial shading from about 8:45 to 10 a.m. And as a result, this graph really shows what is the output of this system from morning hours all the way to sunset. As you can see here, highlighted between 8:45 to 10 a.m., we have a portion of the curve here where you're not getting as much power as you should be getting. So this is really what your PV production will be like without the dynamic peak manager. And this is represented by this highlighted area. And therefore you can see really that you're losing quite a bit of energy that you can be generating or you can be getting from your PV array. Going further, so as mentioned before, the FRONIUS Dynamic Peak Manager is really a low-cost algorithm for MPPT tracking to enable you to get more yield. So how is this happening? So as I said before, for all FRONIUS inverters, this feature of Dynamic Peak Manager is integrated as standard. And it's working intelligently to find what is the optimal operating point, even in the case of shading. As mentioned before, if an inverter is not very intelligent, it was getting stuck at the local maximum power point. But with the dynamic peak manager, because instead of just scanning a partial part of the IV curve, it is scanning the entire IV characteristic every 10 minutes or so, and is periodically adjusting the maximum operating point, and therefore working exactly at the global maximum power point. And at the global maximum power point is really where you're getting the best or optimal output from your PV installation, regardless of shading conditions. So therefore, with the dynamic peak manager as a feature in the FRONIUS inverters, this will guarantee you more yield and more flexibility. More flexibility in the sense that you do not have to worry about unexpected shading. As my colleague mentioned before, there are several possible causes of shading, and some of these are totally unavoidable regardless of how good your design initially was. So you can be guaranteed going forward into the future that when you have a FRONIUS inverter as part of your system, major system component, then you'll be able to get as much yield from your system flexibly regardless of the shading conditions that will happen during the course of the day. So let's look at what you can gain in terms of actual yield by using the FRONIUS Dynamic Peak Manager. So in the previous graph that I showed you, there was an area that was highlighted with the green lines, red lines, sorry, and therefore that represented a portion of energy or power that was not being harnessed or delivered for use to your household or to your factory, whichever the application is. With the Dynamic Peak Manager, you have an additional 7% more yield possible by harnessing or by making the best possible use, like we said before, between 8:45 a.m. and 10 a.m. when the partial shading was happening with this installation. With the dynamic peak manager, then you can get about 7% more yield. So the question would be, what does this 7% really mean for you or for your customer? The answer would be to put it into perspective in terms of figures. And for this, we have considered an installation that is just about 30 kilowatt peak. So a small to medium installation could be for a small factory or a commercial office block somewhere. So 7% more yield in this 30 kilowatt installation would guarantee you an extra 2.4 kilowatt hours per day. If you look at or spread that over the period of 1 year, that means about 2,178 kilowatt hours per day. Over the life of the system, you could basically get, and this is considering a 25-year lifespan, and most systems are actually going beyond the 25-year lifespan. You can get actually just about 54,000 kilowatt hours. And if your cost of power where you are is about 20 cents US dollars, this means over the life of the system, because of using the dynamic peak manager, you can get or you can save about 10,000 US dollars. So the bigger the system is, the more the yield, the more the savings, or the more the earnings for that matter. Going forward, one of the basic design rules, as already mentioned by my colleague, is in as much as possible, try to avoid shading or even remove panels that are shaded on a regular basis. But if this is not possible, of course, the dynamic peak manager is going to help your system to get more yield, and this is at no additional costs, because you'll not need any optimizers, and you're going to look at optimizers in the next slides and see if they are really that useful in a system. So let us look at smart modules, so that we now get into an area where you can start comparing different outputs from different designs or configurations of modules. In extreme shading conditions, or where you have complex systems, on the left here, we have a large chimney that is really casting an unavoidable shadow for a better part of the day over a potential installation area. And to the right here, we do have an installation that is quite complex, with the solar modules oriented in multiple directions. So this would be an ideal situation for you to use what are called smart modules. In the next slides, we will look at what a smart module is, and these are really becoming the norm for quite a number of installations. But for use where there is no potential of shading, then a conventional or traditional module with just a bypass diode is sufficient. At this point, let's look at what are really the key differences. The traditional modules have what is called the bypass diode, and I think a lot of installers or a lot of people know or are familiar with the bypass diodes. But these smart modules have a chip integrated, and this can be integrated at the cell level. So this chip will, of course, because of the technology used, cost you more money initially, but in the long run, this is going to be a guarantee for even more yield regardless of shaded conditions. So the smart chip or the integrated chip becomes a substitute for the bypass diodes, and therefore this also guarantees no hotspots with the solar modules. As you know, hotspots are really one of the killers of the solar modules. And one of the key manufacturers of these smart chips for integration into solar panels is a company called Texas Instruments. So in a conventional panel, let's now try to compare what happens under shaded conditions. So if you have a system or a panel rated at 250 watts output, and one string is affected, just like described by my colleague Cyprian before, the output would be crippled to just about 66% of the output, which is about 165 watts. For a system that is using an optimizer, and this is now an argument that you can use against incurring extra costs to purchase optimizers, you would still have nearly the same output as a conventional panel without an optimizer added on, and therefore you're still stuck at 165% watts with one of the strings in the panels shaded. However, when you have an integrated cell string optimizer, what we are calling the smart modules, each cell is able to self-correct, and therefore this guarantees that the effect of shading on the entire module or array in a PV installation is really isolated to that particular area that is shaded. And therefore, in this particular example, with the same shading conditions as before, you can see that because of using a smart module, then you have a higher output of about 86%. As I mentioned before, the smart modules will of course be definitely more expensive than the conventional module. So it's up to you to consider your particular site and look at whether it really makes any use or is beneficial to use more costly modules. Something else to note is that when you consider using the smart modules and you intend to use FRONIUS string inverters, the DPM function or the dynamic peak manager function needs to be switched off. And my colleague will be sharing a link where you can download the compatibility list for FRONIUS inverters with smart modules. So you can check that from the chat area and be able to download the document from that link provided. Going further, let's now look at the dynamic peak manager versus the DC optimizers. So I think there is a lot of argument for and against the DC optimizers, but in general, what has been studied, and we are going to look at that, an example of such an independent study. In general, what has been studied is that using a DC optimizer in an installation really does not give you that much benefit in terms of the actual system yield. Number one, because of the added components, there is less yield for your system at low to moderate shading, because as you know, the DC optimizers themselves are electronic components, and because of the resistance and this kind of thing, measurements for operations, the DC optimizers are consuming a bit of energy that is produced by your PV array, and therefore that, to start with, results in lower yield from your system. Number two, there is a higher risk of failure, in this sense that the more components you have in a system, the higher the chances that one of the components will at one point or the other fail. The net effect of this is that there will be an increase in your service costs. So you have to make a lot more trips to site to troubleshoot failures, and therefore this for the customer will be a higher OPEX or higher operating costs for the system. Number three, there is a considerable higher risk of fire by using a lot more MC4 connectors in an installation. If you look at the figures below here, we can see from this diagram, all the highlighted red points, these are actually MC4 plugs. In a conventional installation without DC optimizers, you need just about 21 plugs. When you incorporate DC optimizers, you are tripling almost the number of MC4 plugs that you require. There is a possibility that you're going to have a mismatch of the plugs, or some of the plugs are not going to be properly clicked together. This will bring about some loose connections, and with the loose connections or mismatch, you're creating hotspots. If there's a bit of sparking, that is already a higher risk of fire than in conventional installations. Proceeding further, someone could ask, you're talking about using a string inverter versus a system that is DC optimized, but that is just your own argument. But we can guarantee you that this kind of study has been independently conducted. And one of the studies that has been done is from the University of Southern Denmark. And different kinds of systems with string inverters, with DC optimizers were analyzed. And these were done for different shading conditions, as you can see from this example here. And the test conditions were also varied, ground mounted with 42 modules that were divided into different groups. And of course, different scenarios were tested. So this study, for your own reference, to see if it really makes any sense to use a DC optimizer in your system, is available upon request. And we can actually also share the link where you can download the study for your own perusal after the webinar. So what did this study reveal? So in the next slide, we can see a comparison of the yield between a system that has a DC optimizer and a system that is only using the string inverter. So at the no clouds, a very nice and sunny day, the string inverter, maybe as an example, the FRONIUS string inverter with only an inexpensive solution of a dynamic peak manager integrated, is giving you about 18.5 kilowatt hours. And that is about 100% of what is possible from that installation. With a DC optimizer incorporated, you are losing about 2% of the potential output from this system. And if you look at this 2% output loss when the DC optimizer is used over an entire life of the system, plus of course the increased risk factors of failure in the system because of additional components, then you can clearly see that for really low to moderate shading conditions, you do not benefit at all by using DC optimizers. So what is offered by the FRONIUS integrated solution is additional yield even in partial shading, and therefore really we cannot emphasize enough about what is the initial capital of your system versus operating costs, which might be totally avoided. So at this point, we would like to do another poll. Just to get to understand how you overcome these conditions. So the question is, how do you overcome shading challenges? And there are a few choices here to choose from. The first one is module level optimizers, or what you call the DC optimizers. Then the use of smart modules, and you also have another option for something like the dynamic peak manager that is being used in the FRONIUS inverters. And you can also do nothing about it by using inverters that are not intelligent enough. So let's leave the poll on for maybe 20 more seconds to gather your responses. Thank you for your feedback on that question. So as the results are coming through, which I'll be sharing in the next few seconds. So we close the poll now. I believe most of you have had a chance to choose a response. So as you can see from the results, about 8% are familiar with the using of DC optimizers. 33% of the attendees do use smart modules, and 50% are already familiar with integrated softwares such as the Dynamic Peak Manager, and this is really good. And then 8% are doing nothing about it or are not familiar with ways to mitigate shedding for PV installations. I think this is an interesting opportunity where we can say that there is a lot of potential for a lot of installers to sort of do a comparison. And starting with the download link for this independent study done for string inverters versus DC optimized systems, you can start from there and analyze what is the cost of the initial cost of your system, and is it really a very important cost to incur for your customers. So let's proceed. And at this point, let's look at a summary of what we have been talking about in this session. And in a nutshell, what we have said is that good system planning is, and the greatest possible avoidance of shedding is really critical. This is going to guarantee you that you are going to get as much yield from your solar system as possible. So in a solar installation, more is better, yeah? More yield, more earnings or savings, and a system that is more environmental friendly. So the more you get, the better for the PV installation. If these shedding conditions cannot be avoided, then with an inexpensive solution such as the Dynamic Peak Manager from FRONIUS, you are guaranteed a solution that is going to give you as much power or as much energy yield from your system as possible. Going further, and as this becomes more and more common, you can use standard or half cells depending on the particular site conditions, and this can also extend to smart modules as discussed before. But this is going to be guided by what is the analysis guiding you to after you've done a thorough analysis and simulation of operating conditions for your installed system. So, but in a nutshell, with a Dynamic Peak Manager, this is an inexpensive solution. You have less risk of fire because of a limited or a low number of plug connections, and you have also less risk of failure of components because you do not have as many components as when you're using systems with external DC optimizers. So for more information, we are happy to discuss about different kinds of installation procedures, what you need to check, what you need to be aware of when using FRONIUS inverters. But you can go to the FRONIUS website. The downloads section has a lot of resources for installers. And also our continuing webinar series. We have dedicated trainings for Africa region. So you can register for our upcoming webinar events. So, and also we have a lot of resources on YouTube where you can see how to installation videos, and as well as this kind of webinars that we have done like today will also be shared with you, and you can also get them from YouTube at a later stage. For more information regarding our team, we have the contact information displayed. So you can get in touch with any of us via email, via phone. So all the three of us will be very happy to discuss with you whatever pertinent issues you come across when you are designing or installing your PV systems. So, and I think this now brings us to the end of our presentation today. I would like to take this opportunity to thank each and every one of you for taking your time to attend and listening to our webinar today. And we encourage you to also sign in for our other upcoming webinars. We have a series of them planned, as mentioned before, and we will be happy to have you in our next webinars. So we will be closing this webinar in the next few seconds, but we will stay online for about 5 minutes or so to answer any questions that might be open via chat. So you might not be able to hear our voices, but the webinar will continue for the next 5 seconds or so. So I thank you very much, and I'm wishing you a very good day ahead. Thank you.